Hey guys, I start this video with section 10.2 and it's talking about dipole moments. So back in chapter 9 we learned that hydrogen fluoride, which is what I'm showing you here, is a covalent compound because there's sharing of electrons, but this bond is polar because there's much more electron density around that fluorine than there is around the hydrogen. So basically there's a shift of electron density in this molecule. The shift is symbolized by placing a crossed arrow to indicate the direction of the shift. So for example, this right here shows that the electron density is shifting towards the fluorine. The delta sign, this right here, denotes a partial charge. So basically there's a partial positive charge on the hydrogen and a partial negative charge on the fluorine. So let's say we wanted to actually measure polarity of a bond, we would use this dipole moment equation, this right here, which says that mu is equal to the product of the charge and the distance between the charges. Product of the charges Q and the distance between the charges is R. Note that mu is always going to be positive. The polarity of a bond will always be positive. But take-home message here is that the dipole moment is basically a quantitative measure of the polarity of the bond. And here I'm showing you what each of the things are symbolizing, but we've already talked about that. The only thing we haven't talked about is dipole moments. What is the unit for dipole moments? It's a debye. And the symbol for a debye is capital D. 1 debye, and that's spelled, by the way, D-E-B-Y-E. 1 debye is 3.36 times 10 to the negative 30 coulomb meters. So in essence, hydrogen fluoride is a diatomic molecule that contains a dipole moment, and therefore it's called a polar molecule. So now for a molecule that's made up of 3 or more atoms, both the polarity and the geometry will determine whether or not it has a dipole moment. So dipole moment is dependent on 2 things when you have a molecule that's 3 or more. It's dependent on whether there's a polarity between the atoms, and it's also depending on the geometry. So that's why it's very important for us to learn those geometries. Let's do an example. Carbon dioxide. Carbon dioxide, the Lewis structure for it looks like this. I'm going to go a little bit faster now because we should know how to do these Lewis structures. But of course, you would have, everyone has a full octet, and of course the oxygens have 2 lone pairs on each oxygen. Our task here is to find whether or not there's a dipole moment in this molecule. We know that oxygen is way more electronegative than carbon. So the electron shift would be towards the oxygen. So you would have an electron shift this way and an electron shift this way because you have 2 oxygens. The arrows show the shift of electron density from the less electronegative atom to the more electronegative atom. The bond moment, or what we're showing here with the arrows, is a vector quantity. What does that mean? That means that it has both a magnitude and a direction. There's 2 bond moments here in carbon dioxide, but they're equal in magnitude. So that means that the resultant dipole moment would be 0 because in essence both of these oxygens cancel out the bond moment. And this of course makes sense. We know that looking back at our tables for the geometries, this would be a linear molecule. Now theoretically, if we said, okay, what if carbon dioxide was not a linear molecule? Let's say it was instead a bent molecule, something like this, right? Not straight. The resultant dipole, remember, you're going to have a dipole moment going this way and then the other dipole moment going this way. So that means that the resultant dipole moment for carbon dioxide, if it was a bent molecule, would be going down. Okay? But it's not. Remember, this is just a theoretical. Since carbon dioxide is a linear molecule, those electron shifts are going to go in opposite directions, and the oxygens are exactly the same on both sides. So that electron shift is going to be exactly the same pull on both sides from that carbon. Here I'm showing you some more examples. I have ammonia, which we've seen before in the previous video, and you see that nitrogen, of course, has one lone pair and is bonded to 3 hydrogens. The dipole moment between the hydrogen and the nitrogen will be towards the nitrogen because, again, hydrogen is less electronegative than nitrogen, so you're going to have an electron shift towards the nitrogen. But now that nitrogen has that lone pair, so there is an electron shift from the nitrogen to that lone pair, which is signified with this arrow right there. So the resultant dipole moment of this molecule will be going up right here. Now let's try something else. Instead of ammonia, let's try nitrogen trifluoride. Same exact geometry, same exact electron arrangement. The only difference is that we're switching out those fluorines for hydrogens. I'm sorry, we're switching out those hydrogens for fluorines. So now if I look at the dipole moment between the nitrogen and the fluorines, the electron shift is going to go towards the fluorines for each of those fluorines. And then of course you have the electron pair, which the electron shift from the nitrogen is going to go towards the lone pair. So you have 3 vectors going down and 1 vector going up. So the resultant dipole moment, it's kind of like the sum. You're taking the sum of them. And the resultant dipole moment would be going down because there's way more electron density towards those fluorines. It kind of overcomes that electron density from the nitrogen to the lone pair. And you can see, look at the difference in numbers. The resultant dipole, since everybody's going towards the electron pair in the first example, it's 1.46 dBi. But now you kind of have a split in the dipole moments with the nitrogen trifluoride. So it's the dipole moment is only 0.24 dBi. So this is a table in your book. It's table 10.3, and of course it shows that the dipole moments can be used to distinguish between molecules that have the same formula but different structures, which is sort of what I just showed you with the 2 examples previously. You can take a look at those and study them and make sure you understand them. I want to try some examples. So let's predict whether each of the following molecules has a dipole moment. The first example is BrCl. So the Lewis structure would be something like this. And of course we would have the lone pairs, but I'm kind of going to just draw them as lines so it could be quicker. So here, where would the electron shift go towards? The question you ask is which one is more electronegative? The more electronegative atom here is the chlorine. So I am going to have an electron shift going this way from the bromine to the chlorine. So does this molecule have a dipole moment? It should have a dipole moment. So I'm going to go ahead and say yes, it does. Now let's try the next example. The next example would be BF3. So I'm going to draw it. If I did the Lewis structure, it's going to be something like this. All right, I've got my boron and then my 3 fluorines all around it. It's going to take a trigonal planar shape because I've got my central atom with no lone pairs, but I have 3 bonded atoms to the central atom. Now I'm going to ask myself, okay, which one is more electronegative? Well, I know that fluorine is way more electronegative than boron, so I'm going to do my electron shift towards the fluorines, but for each of them, because there's 3 of them, right? So now I ask myself, okay, so does this have a dipole moment? Well, I've got 3 different things, well, actually 3 same atoms pulling in opposite directions. So the symmetry of the trigonal planar shape means that the 3 bond moments exactly cancel one another. So if the forces are equal, the object will basically not move. Think about it like that. Consequently, if BF3 has no dipole moment, it's a nonpolar molecule. There is no polarity here because everything, all of these vector quantities, all of these dipole moments cancel out. So BF3 does not have a dipole moment. What about the last one? Methylene chloride. This Lewis structure is similar to what we saw before for methane. So if I did the Lewis structure, it would look something like this. You would have your carbon in the middle, and then you will have a Cl, and then you have those two H's. So I'm going to put one towards the front and one, oops, excuse me, I made that ugly, but you would have one towards, let me erase that, you would have one towards the back, one hydrogen towards the back. Now we ask ourselves, does this have a dipole moment? Well, where does the electron shift? There, first of all, you have two chlorines, so we know that chlorine is way more electronegative than carbon, so I'm going to have an electron shift going towards the chlorines, both of them, and then I'm going to have an electron shift going towards the carbon because hydrogen is less electronegative than carbon, so I'm going to have an electron shift going this way for these atoms. So what would be my resultant dipole moment? The resultant dipole moment would then be basically towards the chlorines. So I would have something like, I would believe would be something like this. So that would be your resultant dipole moment. So if it has a resultant dipole moment, that means that this is a polar molecule. There is an electron shift generally towards the chlorines. In essence, the bond moments do not cancel out, and the molecule does possess a dipole moment. So the take-home message is that dipole moments or bond moments are resultant from geometry and the polarity of the bonds. All right, the next topic I want to talk about is valence bond theory. All right, so the Vesper model was based largely on Lewis structures, and it really provides a straightforward method for us to predict the geometry of molecules. But the Lewis theory does not clearly explain why chemical bonds actually exist. For example, the Lewis theory describes a single bond between two hydrogen atoms, HH, and two fluorine atoms, FF, as exactly the same as the pairing of two electrons. Yet these two molecules, have very different bond enthalpies and bond lengths. So the single bond between these two different molecules are not exactly the same. So what does that mean? That means we need more theories. So that's when we came up with the valence bond theory, which assumes that electrons in a molecule occupy atomic orbitals of the individual atoms. So again, Lewis theory describes HH bond, single bond, simply in the terms of electron pairing. But the valence bond theory describes the HH single bond as an overlap of two 1s orbitals. And by overlap, I mean they share a common region of space. But what happens when these two hydrogen atoms move towards each other? The whole point of this theory, this valence bond theory, states that stable molecules form. Why do they form? They form because the potential energy of the reacting atoms is less than if they were apart. That's the whole point for things coming together. And that coincides with, remember, filling the octet, because there's less potential energy to be together than to be apart. And here is a graph showing you of what's going on. Initially, when the two atoms are far apart, there's no interaction whatsoever. So we can say that the potential energy is basically zero. As the atoms approach one another, each electron is attracted by the nucleus of the other atom. But at the same time that this is happening, the electrons are actually still repelling each other. While the atoms are still separated, the attraction is stronger and stronger and stronger than the repulsion that they feel. So the potential energy of the system actually goes down. And of course, this trend continues until the potential energy reaches a minimum. And that's the point where it's the lowest potential energy and it's the most stable. And this situation corresponds to the overlapping of these two 1s orbitals for this molecule. And here, I'm showing the change in electron density as the two hydrogen atoms approach each other. You can see that this concept of overlapping orbitals applies equally well to other diatomic molecules. So FF single bond, the fluorine single bond, forms when two p orbitals overlap, not two s orbitals, two p orbitals. And similarly, HF, hydrogen fluoride, is the overlap of one s orbital for the H and the two p orbital in the F. The valence bond theory does account for the changes in potential energy as the distance between these atoms change. And because the orbitals involved are not the same kind, in all cases, we see why the bond enthalpies and the bond lengths of all these different molecules might be different. We're going to learn about hybridization in the next video, and you're going to learn to understand what I mean a little bit better when I talk about this. Alright, see you guys later.